Okay, welcome to note set number 13. Here we're going to get into some basic sampling theory. So this is covered in section 6.1 of the textbook. It's covered differently than the way that I cover it. I cover it my own interesting way, which I think, well, I personally think it's better, but I suppose maybe Proacus and Monolacus might disagree, but anyway, this is also identical to how I present it in my Signals and Systems class. So this should be a review, but it's kind of crucial that you have this understanding before we go into the more advanced ideas in sampling theory and some of the issues that you encounter in real-world sampling. Okay, so I will go through this somewhat quicker than I would in my Signals and Systems class, but that video is available to you, and if you need it, you should go back there. Okay, so basically, what we're looking for in a DSP system is we need an A to D converter to create our discrete time signal to drive into our DSP computational system, whether it's an actual computer or just some hardware dedicated to doing DSP, doesn't really matter. And then in some applications, but not all, we need to reconstruct to get back a continuous time signal. So all of this is predicated on the idea that that these samples right here have all of the information that would be available in the continuous time signal itself, at least in theory. And so to establish whether we can actually make samples that completely and perfectly represent a continuous time signal, and under what conditions can we do that, we remove this part. So if we take out any processing and just simply take the samples and then immediately run them through a DAC and get back some signal, which for now we'll call x hat of t, and we want to ask the question, can we make x hat of t equal to x of t? And if we can answer that yes, then we know that the samples completely represent x of t, and we don't lose anything, at least in theory, going to digital signal processing. So that's what we're to establish. So, in the real world, you would never take these samples and then immediately apply them to a DAC. It just wouldn't really make sense to do that. But here we're going to take a look at this. And, well, I see this figure here is a little washed out, and I apologize for that. But hopefully you have it on your notes, and it should show up a little bit better there. But the basic idea is we've got some x of t, which is this continuous curve. We've got an A to D converter, which is basically just taking samples of this function at various points, spaced t seconds apart, or equivalently taken at a rate of fs is equal to 1 over capital T samples per second. And then the idea is we take those samples and we put them into a D to A converter. And the basic idea of the D to A converter is each time it gets a new sample, it generates a pulse at the appropriate time. So if you get a stream of samples coming in, you'll get a stream of pulses coming out. So here you can see the stream of pulses. The height of each pulse is just the height of the sample that it corresponds to. The position of the pulse is the position of where that sample was taken. And so the distinction, let me clear off some of this stuff, the distinction between the samples and the pulses is that with the samples, there's nothing in between. It's not like it's zero in between. There's just no value. So the samples are just a series of numbers. Whereas down here, the stream of pulses, in between the pulses, it's actually zero. It's a continuous time signal. And so that's the key distinction. And then we take that stream of pulses, and we will see that if we run it through an appropriately designed continuous time low-pass filter, then that's going to be how our DAC works. And we'd like to be able to figure out how to do this pulse generator, how to do this CT low-pass filter to make this thing equal this. And that's what we're after. So our math model for sampling is very, very straightforward. We just say the nth sample is just, you take this and you evaluate it at the time nt. So it's literally just x evaluated at nt. And here you can see the value of using parentheses to show the continuous time signal and square brackets to show the discrete time signal. That way we know that is the continuous time signal evaluated at the time nt. So this idea of holding here, doesn't have an awful lot of physical meaning. It just, we're sampling and we're creating a number, and it's just stored. We can think of that as just stored into memory. That's it. So let's talk a little bit about the math model for the DAC. So we said that there's a pulse generator, there's a filter involved. The filter is going to be made up out of transistors and op amps, resistors and capacitors. The pulse generator probably also made up of transistors and so forth. So if we think about what's happening here, if we think about this pulse generator creating or working with a prototype pulse, so at time equal to 0, it would create this little rectangular pulse, P of t. If it gets a sample that had been taken at some later time, it will create that pulse at a later time. So the pulse generator is just basically creating time-shifted versions of that little rectangular pulse. And the amplitude, the height of that pulse, is multiplied by the sample value. So here we're just using the fact that the nth discrete time sample is the sampled value of the continuous time signal at the time nt. And so now, so that's this is our time domain model for this x tilde of t, which is halfway through the DAC. And we have a nice little picture of it over here. You can see that, as the samples come in, we just create this little pulse train. So we go that high, then we go that high, then we go that high, and it's 0 in between those little pulses. And right now we're just assuming that the width of the pulse is some number that's smaller than the sampling spacing, capital T. Okay, so we can visualize what x tilde of t looks like in the time domain, and now we need to send that thing through this continuous time filter, which is easiest to analyze in the frequency domain, as is almost always the case. So the Fourier transform of x hat of t, the output of the DAC, will just be the Fourier transform of x tilde times h of omega, the frequency response of that continuous time filter. So to figure this out, how this works, we need to figure out what is this thing. So in other words, we need to analyze this signal in the frequency domain. So we need to take a Fourier transform of that. Now, before we do that, we're going to make one simplifying change. We're going to say, well, we need these pulses to be these narrow rectangular pulses, and we remember that if we think about a rectangular pulse going narrower and narrower and narrower, but we let the height go to infinity, we get the delta function. So we're going to use the delta function instead of these rectangular pulses. We'll later see that we can easily account for real life pulses. But the reason that we do this is it really simplifies the analysis at this point. So it strips away any of the hard or harder things or hardest things and simplifies the analysis. So at this point, our x tilde of t, well, I guess we'll go here. Will just be x at nt times a delta function at nt. And by a property of the delta function, we can actually pull this out in front and just replace it with x of t, so that each one of these things, when it multiplies this function at its location, will just simply extract that value. In between the delta, this delta pulse strain is 0, so it doesn't have any effect. So that's setting this up. And so now to visualize this rather than how we had it before, we can think about this x tilde of t here halfway through the DAC as if we're taking x of t, multiplying it by this what we call an impulse train, which is this thing. And so that's just a sum of a bunch of shifted delta functions. So for n equal to 0, it's just this and then this delta function. For n equal to 1, it's this and then this delta function. So each one of these terms in the sum is 0 when any of the other ones, well, let me say it this way. If we sum up those terms, there's not really any interaction between them. So so we get this impulse train. And then the last thing we imagine is taking x of t times this impulse train, and we can visualize that this way. Now, just a word of caution here. Remember, these delta functions in this impulse train, they go to infinity. So they have a height of infinity and a width of 0 and an area of 1. I know, a really weird, bizarre thing, but that's what we're working with here. So when we show them on a diagram like this, the height is not, that we show graphically, is not the physical height of the delta function because it goes to infinity. What we're really showing is a representative of any number that's multiplied by the delta function. So in other words, when we multiply a number by a delta function, it doesn't change its height, it changes its area. So this is just a graphical way of visualizing. This would be some number bigger than 1, perhaps, multiplying a delta function. And that's just how we visualize that. So this thing down here, this x tilde of t, is what most books will refer to as the impulse sampled signal. Proakis and Manolakis, I'm sure, refer to that. And the problem that I have with most developments of sampling theory goes is that they tend to allude to the idea that it's this impulse sampled signal that comes out of the A to D converter. But it's not. It's actually more appropriate to think of that inside the DAC, although in reality this impulse sampled signal never actually happens anywhere in the real world, as we'll see. But for right now, we're imagining that we have this ideal DAC that has an impulse generator, and that impulse sampled signal occurs halfway through the DAC. And that's the thing that we need to analyze. So if we can analyze this thing in the frequency domain, then we can figure out how it goes through this filter and see what we need to recover x of t from the samples. And that's what we're after. So our goal is to determine how do we set things up so that x hat of t, the output of the DAC, is equal to x of t, the input to the ADC. So our approach is we've got this x tilde of t, we're going to find its Fourier transform. We're then going to imagine taking that Fourier transform, multiplying it by h of omega to get the Fourier transform of the output of the DAC. and then look to see what we need to do to make those things equal to each other. So that's our approach. So we'll do this in several steps. So the first step is we look at this delta sub t. This is our impulse train that gets multiplied by x of t when we think about the impulse sampling. So we look at that thing and we go, all right, it's periodic. So it's a continuous time periodic signal. So we can write that out in terms of a Fourier series. And this set of steps here, I'm not going to go through the details, but that set of steps finds the Fourier series coefficients. And what we find is that for every value of k, c sub k is equal to 1 over capital T for every value of k. So that means that we can then write, we replace this c sub k by 1 over t, and we get something that looks like that. And look at what we're angling at here. What we're going to do now is take this and multiply it by our x of t. And so what we're doing is simultaneously accomplishing, we're showing that that impulse sampled signal will look like the original signal plus a whole bunch of frequency shifted versions of that signal. So this is where the insight really comes from, right there. So if we go on, we see that actually happening. We have our x of t times that impulse train, which we then replace by its Fourier series. And then we bring the x of t inside. We'll ignore a few squawks from the pure mathematicians who say, well, that doesn't always hold, but we'll ignore that and say we're engineers. It will hold in all the cases that we're interested in, and we don't care about the idiosyncratic cases that the mathematicians can trump up and say, it doesn't hold there. Well, okay, fine, we're not interested in that case. So we bring it inside, and now we see that we have a bunch of frequency shifted signals. So now we take the Fourier transform of this, we pass the Fourier transform through the sum, and we know what that does in the frequency domain. That multiplication by the complex exponential does the frequency shifting. And so what we see is that the signal halfway through the DAC, the impulse sampled signal, consists of a sum of a whole bunch of different spectra, one of which is the original signal spectra, and then the others, let me clear that off here. Oops, not letting me clear that off. I don't know why. Let's see what we can do here. There we go. So we've got our original, and then we have a whole bunch of frequency shifted versions. Each one of those is just one term in the sum. Each one of those comes from taking the Fourier transform of one term in this sum. So we've got the original, and we've got a bunch of shifted replicas, and our goal is to make sure that those shifted replicas are kind of safely out of the way and don't interfere with our original spectra, so that we can go in and snatch out that original and somehow get rid of all these shifted replicas. And that's what that fill inside the DAC must do. So the thing that we must do is be able to isolate that and then get rid of all of these different terms by using this low-pass filter. And so to see that, let's just take a nice picture here. Suppose we have this nice band-limited triangular spectrum. I love the triangle spectrum for explaining ideas. It's one of my favorite shapes to draw for explaining this. We're saying that it's band-limited to b hertz. And so what we get here, we look at the spectrum of that thing. Let me clear these things off. We look at the spectrum here, and we see our original, and then we see a bunch of shifted versions of those. And remember, they are shifted by multiples of fs. So when we see that, we can quickly realize that what we need is this edge to be above this edge. Well, I didn't quite draw that exactly right, but let me see if I can erase that here and draw it a little bit better. So I need the first edge that I drew to be above the second edge that I drew. And if you look carefully, you can puzzle out that the edge on the left is at frequency B, the edge on the right is at frequency Fs minus B. Therefore, we need Fs minus B to be above B. That's what we state here. And if we swing this B over to the other side, we get that Fs must be greater than 2B. If that happens, if we set that up such that that's the case, then there's no overlap. The spectral replicas do not overlap the original. And what that allows us to do then, we can see here. Here's the case we were just looking at. We don't have any spectral overlap here. So we have our spectral overlap doesn't happen here or here. And so now we can apply this filter. Now listen carefully. I've left this off the slides, but the cutoff frequency of this filter in here, so the cutoff frequency of f sub c is always equal to Fs over 2. So we're cutting that off, and since this edge is shown to the right of that, these will get eliminated, these will get eliminated, and we're left with something like that. And so as long as there's no spectral overlap, then we can perfectly reconstruct, we can extract the original signal spectrum. We can perfectly throw away all the spectral replicas, and we get back the original spectrum, which means that this x hat of t will be exactly equal to x of t. But now look at everything that we had to say here to make that happen. So we needed quite a few things to happen there. We needed a signal that was perfectly band limited. So outside of some frequency B, its spectrum was exactly equal to 0. And we also talked about an ideal filter here. So even though this is a very nice result, it is not saying that we can really do this perfectly. There are some practical constraints, but the reality is that we can do this so well that it works almost perfectly. And you tell me how much more perfect you want it to be, how much closer to perfect you want it to be, and we can always make it that much closer to perfect. It just may take a little more resources, faster sampling, more complex and expensive filter design, and so forth. We can never make it exactly perfect, but if you want it a little bit better, just pay a little bit more money, and we can make it. So. All right. So let's go on slide here, and so this is just summarizing what we just saw. That at least in theory, that's why it's called the sampling theorem. If we have a band-limited signal whose highest frequency is B hertz, we can completely define it in terms of its samples, completely and perfectly defined in terms of its samples, as long as we sample at a rate that is Fs greater than or equal to 2B samples per second. And just a word in passing here. Notice that Fs is a sampling rate, and we are talking about its units as samples per second, but also remember it's that Fs that's shifting the spectral replicas, or our spectral replicas get shifted by Fs and 2Fs. So we should also interpret Fs as just a regular continuous time frequency in hertz. So sometimes you'll hear people say, my sampling rate is such and such samples per second, and then other times they'll say such and such hertz. So same kind of thing. But this is a big idea, and it's the basis for almost everything that we find exciting and interesting today as far as cell phones and CDs and MP3s and so on. Now, what happens when things go a little bit wrong? If I don't sample fast enough, even if I have a band-limited signal, if I don't sample fast enough, now I'm going to have the spectral replicas overlapping the original spectrum. And then when they add together, the black line here is the sum of all the dashed red lines, one dashed triangle is the original spectrum, and all the other dashed triangles are the spectral replicas. But when you add them together, you get something that doesn't quite have the triangular shape. In this case, it goes flat over part of the region where it should be going down. Then we apply our filter to that, and we end up getting something that does not at all look like the original signal spectrum. So in that case, this would not be equal to the input signal. And that's simply because we did not sample fast enough. Our sampling rate was less than 2B samples per second. So that's what happens when you have a still ideally band-limited signal, but you don't sample it fast enough. You get aliasing. And if you remember way back in, I think maybe even the first or second set of notes, we talked about aliasing from the point of view of sampling a discrete time, or creating a discrete time sinusoid. Same kind of idea. In fact, it's the same idea, just in different. What if the signal's not band limited? So in reality, no real world signal is ideally band limited. They all have spectra that have this characteristic. They don't go down to zero and stay at zero. They kind of go down close to zero and stay close to zero. So what impact does that have? Well, if we look at what happens with the interrelation between the original spectrum and the spectral replicas, we see that because of this tail here, we end up getting lots of stuff, quote unquote, folded back in to our region of interest, which would be minus pi to pi on the discrete time axis and minus fs over 2 to fs over 2 on this f-axis. So in this case, because this never goes exactly to zero, no matter how high I set my sampling rate, there's still going to be some amount of aliasing. Now, one way to attack this problem is to just say, well, how far out do I have to go before this thing drops down so small that I don't really care about it anymore? Okay, set that as B, now sample at twice that. Well, that's one way to do it, but sometimes that sampling rate becomes excessively large, and so there is another way to deal with that, and that's by using an anti-aliasing filter. So we'll illustrate this for the point of view of music. So we've got some music going into a microphone, and you may know that humans can't really hear audio above right about 20 kilohertz or so. So if we run our signal through an anti-aliasing low-pass filter first before we sample, so here's just a cartoon version of an anti-aliasing filter. So there is this stuff out here that could fold back in and alias into frequencies that we could hear if we just sampled this at a rate, say, twice 20 kilohertz, or just a little bit more, say 44.1 kilohertz. So, so that could be a problem. So the effect of the anti-aliasing filter is that we suppress the content above, say, 20 kilohertz or so. And so now, instead of seeing this tail that could be significant, we still see a tail, but it's quite a bit less significant. Now, keep in mind, with real-world filters, we cannot make that go to zero and stay at zero. So in both cases, here and here, we still have something above 20 kilohertz that's not zero, but after the anti-aliasing filter, we've pushed it down even farther than it was originally. Then we do our sampling, say at 44.1 kilohertz. We end up with a scenario like that. You can see the dashed line there, but that dashed line is at this level. And so presumably we've used the anti-aliasing filter to push that down so far that it's negligible. So I'm going to skip over this pretty quick, just some terms that you should be familiar with, define these in signals and systems. So you should be familiar with concept of sampling rate, the fact that we talk about it in samples per second, but also sometimes in hertz. You should know the Nyquist rate is the minimum sampling rate of 2B. When we sample at the Nyquist rate, it's called critical sampling. If we sample faster, it's called oversampling. If we sample less, it's called undersampling. And generally, we don't want to undersample. As we just saw, if we sample too slowly, we will have aliasing. But we will soon see that in some circumstances, we can actually use undersampling to our advantage. And we'll see that when we get to something called bandpass sampling. And also, critical sampling, I mean, it's really just a theoretical notion. In the real world, we just simply cannot do real critical sampling because we would need an ideal low-pass filter. That's just a term for for the textbooks. And this just summarizes what we just saw, and so I'm not going to go into it in any great detail. So that finishes up this set of notes, and we'll see you in the next set of notes.